yesterday's lecture we learnt about the premixed flame, right. So, first we are going to the introduction and then we will see the non-reacting laminar jet and the solution for the non-reacting laminar jet basically, the reacting laminar jet diffusion flames and then the conserved scalar approach, right, and the counterflow diffusion flames. Okay. So, these are the topics which are going to cover in this lecture. So, as we are all familiar with this picture, so this is the premixed flame and on the right hand side you have the candle flame which is basically the non-premixed or diffusion flame. So, you see that the fuel and oxidizer they are on the same side in the premixed flame, whereas that is not the case for the non-premixed flame. Okay. So, they are separated and then they are brought together by the convection and the diffusion. So, the molecular mixing becomes very important and then when they are mixed at the proper proportion, then there is a flame that is manifested by the high temperature, and also you can see that the reaction rate that occurs near the at the maximum temperature location. So, some of the applications of the non-premixed flames are in the gas turbines and then you can also see in the rocket engines and also in candles. Okay. So, there is one experiment, I mean you can see that one person who is basically taken the kerosene in his mouth and then he is blowing it up, and if you can ignite that, then there is a flame. So, that is the flame that you can see. Okay. So, these are basically the examples of the non-premixed flame which we can enter, but although I think most of them are not laminar, but these are the examples. So, for example, in the gas turbine and in the rocket they are basically in the turbulent region, also that is also a turbulent flame. Okay. So, some of the common diffusion flame that we can establish in the lab, okay, and then we can study that, and we can carry out the experiment in the laminar regime. For example, the jet diffusion flame, right. So, we can carry out an experiment on the jet diffusion flame and there will be a flame that is represented by the stoichiometric mixture fraction or the equivalence ratio 1. So, this could be the flame surface, right. Similarly, you can carry out the experiment that is basically a counterflow diffusion flame. So, you have fuel and oxidizer, they are basically separated from each other and the fuel and oxidizers are entering from the opposite directions, and depending on the momentum they carry, right. So, if the momentum of these two streams are equal, then there will be a stagnation point in the middle, right. But depending on the stoichiometric ratio of your fuel and oxidizer, you can have a flame at a different location, right. So, in most of the cases the stoichiometric mixture fraction, we will study what is mixture fraction and we will see that what is the stoichiometric mixture fraction in subsequent slide. So, then it can occur towards the oxidizer side, right. So, if the momentum is same, then the stagnation plane will appear at the middle of the domain, but if the momentum of these two streams are different, then the stagnation plane can also shift, right, and depending on the fuel air ratio, the flame can be located either here or in this side, right. In most of the hydrocarbon flames, the stoichiometric mixture fraction is very close to 0, right. I mean, it is almost around 0.05, 0.06 like that, right. So, it appears towards the oxidizer side. Okay. That is one observation we had, right. So, this flame location, it depends on the fuel air ratio, right, and what I would like to say is that you can carry out the experiment and you can measure the concentrations of different species along a streamline, and then you can come up with a very good flame structure. So, flame structure means now if you can measure from here to here the concentrations, you will get in terms of physical coordinate, right. Now, if you can come up with the mixture fraction from these concentrations of different species, right, then you can get a very good flame structure. Then you can represent all these variables like temperature and the species concentrations in terms of mixture fraction. Okay. So, that will give you some idea about the flame structure. We are going to see that when we will talk about the counterflow diffusion flame. Okay. Also, there could be a spherical diffusion flame that can appear on from a drop, so single droplet experiment you can conduct, and then there could be a spherical flame surrounded by the spherical droplet. Okay. So, now the important thing is that the diffusion flames are safer, okay, since the fuel and air are separated, right. They are not mixed, unlike in the premixed case. In the premixed flame, the fuel and oxidizers are already mixed in the molecular level and then they reach the flame front, but here they are actually separated in the non-premixed or diffusion flame. And wide range of operations, and hence, I mean, these flames are very stable, you know. So, it is not restricted by the flammability limit. Okay. So, if you can consider that this is the jet that is bringing in the fuel. Okay. So, what will be the equivalence ratio at the exit of the jet? Can anyone say? What will be the equivalence ratio here at the exit of the jet? Infinite, right. And the equivalence ratio at the outer portion, that is in the co-flow, what will be the? It will be 0. So, you can see that the equivalence ratio will vary from infinity to 0, right. So, you can see a wide range of mixture, and depending on the flammability, so they can burn, right. So, that is one of the important features of the diffusion flame. So, you can get a mixture with different equivalence ratio, whereas in the premixed flame, which we have seen that we have a fixed equivalence ratio that is decided by the proportion of the fuel air, right. But here depending on the mixing, you can get a range of equivalence ratio. So, in this lecture we are going to talk about the laminar flames only. So, the turbulent flame also already Professor Poinzo is talking about. So, we are not going into that. Now, separate feeding of fuel and oxidizer takes place into the combustion chamber, and you can see that these are happening in the diesel engine, jet engines. Okay. And how the combustion is taking place, that is a very crucial question that we have. So, what is that is basically responsible for this combustion in this case. So, initially there is a mixing, and then when the fuel and air are mixed thoroughly, then there could be a combustion, right. So, first you need to mix the fuel and air, and depending on the stoichiometry, there could be a flame an intense region where the maximum amount of heat release can take place, and hence you can see a flame and with a very high temperature. Okay. So, mixing is basically by convection and diffusion, but the diffusion plays a very crucial role, and it is on a molecular level. Okay. So, when we are talking about the laminar non-premixed flame, the molecular diffusion plays a very important role. We will see that in the turbulent diffusion flame, we have both molecular as well as the turbulent diffusivity, that is the governing criteria. So, now simple examples of the diffusion flames are candle flame, right. So, we all know about this, so we are not going to that. So, what we can see that when you light up a candle, you can see that there is a dark region where the paraffin that is coming from the candle, it is getting evaporated, and then after that there is a flammable region. Okay. And you can see a yellow region that is basically containing the soot particles, right. So, another important aspect of the diffusion flame is that they are very much sooting, unlike in the non-premixed, unlike in the premixed flame. If you are operating the lean condition, you can avoid soot there, but here you have a wide range of equivalence ratio, and then the chances are there when you have a more fuel concentrations at those locations, you can have enough soot productions. Now, we will see that these soots, they travel downstream, right, and when they get enough oxidizer that is coming from the surrounding, they can partially oxidize. Okay. So, that can also take these soots can partially oxidize when it comes to the area where it can find more amount of oxygen, but some of them can still remain in the system, and then it can come out from the exhaust, right. So, soot particles, they are basically formed in the fuel rich regions of the flame. As I said, they occur in the fuel where you have the more concentrations of the fuel, right. Now, this soots that is getting produced, they can, I mean, typically it can appear like this. So, this is the appearance of a soot distributions, and you can see that often there is a break here, right. Okay. So, then the soot particles can come out, and this is basically called the soot wings, and if you can see here you can see on the right hand side there is a soot wing that is basically formed here. Okay. So, if the residence time of the soot particles in the region of oxidizing environment is larger, then these soots can eventually get oxidized, but otherwise they will, if they are not getting oxidized, then your flame, I mean you can have enough amount of soots produced, and then that will be not desirable actually. So, now we will quickly go to the non-reacting laminar jet. There is no reaction. So, what is happening, we have a jet that is coming out, and then what do you see, that at the end of the jet you see a potential core, right. So, what is a potential core? So, any idea? Do you know about potential core? There is no viscous effects, right. Okay. So, the potential core is that where you do not have any viscous effects, and the flow is morely the potential, and there is no change in the velocity within this region. Okay. So, the velocity from here to here will not change very much, the same as the concentrations that we are going to see. So, now what is happening, this jet is coming out and then it is spreading. Okay. So, this is represented by the jet edge. Now, if you can take sections at sufficiently away from the potential core, right, at x equal to x1 and x equal to x2, you can draw the velocity profile and the concentration profiles, right. For example, at x equal to 0, your velocity may look like this, right. So, if you have the uniform jet velocity at the exit, right, represented by this top hat profile, so you can get this top hat kind of profile there. Okay. So, now if you go sufficiently downstream, you will see that there is a diffusion that is taking place, right. So, the jet is basically spreading, there is the surrounding air that is getting entrained into the jet, and although the momentum remains conserved, but you need to conserve the momentum, right. But in order to conserve the momentum, since you are gaining the mass from the surrounding, your velocity has to drop, and that is why you see that the velocity at the center line decays downstream, and if you are going further downstream, you see the more and more decay of the jet. Okay. And at the same time it spreads. This can also be seen if you plot along this center line. Okay. So, up to the potential core, you see that there is no variation in the jet velocity, and after that it decays, the center line velocity it decays. Okay. So, if you can assume that the Schmidt number, right, the Schmidt number is a ratio of the what is Schmidt number? Okay. So, if the Schmidt number is unity, then you have the momentum and the species diffusivity both are same. In that case, you can, if you can normalize the jet velocity by the exit velocity, suppose the jet exit velocity is v, and if you can normalize the jet velocity, so you are basically plotting Vx over Ve, right. You are plotting Vx over Ve, then it is maximum unity at the z exit, and then it remains unity up to the potential core, and then it decays. So, you can observe the similar trend for the species concentrations. So, for the unity Lewis number, unity Schmidt number, you can see the similar profiles. Okay. Now, we are going to analyze this type of this laminar jet, which is basically non-reacting. So, there is no density change in this, right. So, as I said that before discussing the jet flames, we will analyze the non-reacting laminar fuel jet, because it can give us some idea about how the reacting jet can look like. Okay. So, understand the basic flow and diffusional process. So, these are the things which we are going to learn from this exercise. Okay. So, we will understand the basic flow and diffusion process in the absence of the chemical reaction. Later we can incorporate the effect of the chemical reactions. So, we have the circular fuel port, and we assume uniform, that is the top hat velocity profile at the exit of the tube. Okay. So, initial jet momentum, as I said, it will be always conserved. Whatever distance you go downstream, the momentum has to be conserved, right. So, the initial jet momentum you can express like this. So, this is a jet momentum. Suppose you take a cross section here and you integrate from center line to the infinity, right. So, 0 to infinity you are carrying out the integration. So, within this square bracket you have the mass flow rate, right, and you are again multiplying it with the axial velocity, right. So, this is the momentum flow rate. So, that has to be equal to the momentum that is coming in, right. So, that is nothing but rho times pi r square. So, this is area times velocity, the mass flow rate multiplied by V. Okay. So, this is the axial momentum that will remain conserved. Okay. Similarly, you can calculate the initial jet fuel mass that is coming out, and in the absence of reaction, the fuel mass whatever you are sending in, that will also be conserved, isn't it. So, you can write down the expression, and so this you can integrate at any locations from 0 to infinity. So, this is the mass flow rate, and you are multiplying it with the fuel mass fractions at that location, right, and you are carrying the integration 0 to infinity, and that has to be equal to the initial fuel mass that you are injecting into the system. Okay. So, there are some assumptions which I have listed. So, it is a 2D axisymmetric and steady flow that we are going to assume, and constant pressure. Okay. So, in the most of the open jet case, I mean the pressure remains constant, and at the same time we will assume that there is no reaction, so temperature is also constant. Further, we are assuming that the same molecular weights for fuel and oxidizer. So, the jet is basically fuel, although it is not reacting. So, there is a fuel and then surrounding by the oxidizer, and we are assuming that the fuel and oxidizer molecular weight are equal, and therefore, we do not have to invoke the ideal gas law to calculate the gas density, right. The density will be uniform everywhere. The simple binary diffusion of species, right, and then momentum and species diffusivities are equal. That is what I said, the Schmidt number is unity. So, momentum over mass diffusivity, that is unity. Only radial diffusion is important, right. So, in this type of flames, the diffusion in the radial direction, that is important, and you can neglect the diffusion in the axial directions, right. However, this solution will be valid after some distance downstream of the nozzle exit, that we are going to see that. Okay. So, let us start with the governing equations. So, we are all familiar with this. So, now we are dealing with a circular jet. So, we are writing the equation in a cylindrical system. So, the mass conservation equation, and then we have the species conservation equation. So, there is no reaction rate source term, and the third one is the axial momentum conservation equation. Okay. So, here you see that there are several unknowns. The unknowns are the axial velocity, radial velocity, and the fuel mass fractions. Okay. So, we can solve it easily, isn't it? We can solve it easily. We have the boundary conditions. So, along the jet center line, okay. So, this is the center. So, this is the center line of the jet. Okay. So, what type of boundary conditions we should use? A symmetric boundary condition, right, and we know that at the inlet what is the boundary condition. Okay. And again we have to, so if you see that this type of equations, we need 3 boundary conditions. Okay. So, another we will impose at the far from the jet center line. Okay. So, r tends to infinity, so large radius. So, there actually we expect that the flow has to be quiescent. So, the velocity will be 0 and there is no fuel. Okay. So, as you are all know that along the jet center line r equal to 0, we have the symmetric boundary condition, and it is basically the gradient of the radial gradient term is basically 0. At the jet exit, we have the top hat profile for the velocity and the fuel mass fractions. So, if you can solve them numerically, you will be able to obtain the Vx, Vr and Yr. Okay. But we have the, fortunately we have the analytical solution for that, and this is basically just like the boundary layer theory, in that we assume a similarity variable and then we can solve this. So, here also we have this similar approach. So, I will just quickly browse through that because it will be very lengthy if I want to go through each step. So, we assume this similarity variable zeta is equal to C times R over X, and then if you carry out this differentiation, and then the stream function is defined like this in this case, right. We have to see that whether this stream function is satisfying the continuity equation, that we will eventually see. Okay. So, if you know the stream function, you can calculate the radial velocity. So, radial velocity will be minus 1 over r del psi del x. So, you can carry out this exercise and you will get this expression for the radial velocity. Similarly, the axial component of velocity Vx will be 1 over r del psi del r. So, if you follow the same exercise, you will be able to get the expression of the Vx. Okay. Now, we can put these definitions of Vr and Vx in the continuity equation and see that whether it is satisfying the continuity equation or not, right. Okay. So, first we will find out this term del Vx del x. Okay. So, it is a long it is a somewhat long expression. So, after this exercise you will be able to obtain this value. Okay. Next is that the other term, that is 1 over r del r of Vr times r. So, you after the exercise you will get this, and now this is your the continuity equation, and you see that if you plug in these numbers you will get it is 0. Okay. So, your stream function and is satisfying the continuity equation. Next we will move to the axial momentum equation, okay, and we write the term by term and we can expand this. So, I will be sending the slides, so I am not going through this. So, you will get the different terms of the axial momentum equations, right, and then finally you will be able to get this type. I think this is the another term, and the final form after all this exercise you are getting a simple equation. Okay. So, this is one ODE. Okay. So, you have come initially you had a PDE, and then from that you have reduced it to an ODE, and you have the boundary conditions for this. Now, you can solve this ODE, and the solution is this. Okay. So, when you know this solution F, you can always recover the radial velocity and axial velocity. So, that is what we usually do. Okay. So, the axial velocity Vx, we initially had this expression. So, now we need to we recovered F, right. So, we can differentiate this and get this expression df d xi. So, df d xi will be like this. Okay. So, finally, your Vx becomes this. Okay. So, you can do the similar exercise for the radial term. So, initially you start with this expression which we have already derived before, and you just plug in the value for f, and final expression is this one. Okay. So, now you can calculate the jet momentum. Okay. So, you can calculate the jet momentum. So, jet momentum is this, right, and then you can simplify this. I mean, you need to replace it in terms of this these derivations. Okay. And finally you will get the constant c, right. This constant is given here. Okay. So, when you know this c and other numbers, you can get the solution. So, your Vx becomes this. So, this is the final expression for the axial velocity, and the radial component of the velocity will be like this. So, what is important? We have the Je, that is the initial exit, the exit momentum of the jet, that we know already. And what is this? This is the similarity variable. For that we have the expression here, right. So, this similarity variable contains the dependencies on r and x. Okay. So, we have the two dependent variables. So, you can obtain this value at any physical locations within your domain, right. When you know this value, you can put it here and you can recover the axial and the radial component of velocity. Okay. So, now you can normalize this velocity, the axial velocity, by the exit velocity of the jet. So, V is the exit velocity of the jet. So, you can do the normalization, and then you get a very beautiful expressions. Okay. So, what it says, so there you get a Reynolds number dependence, right. It is important to note that this here actually I have defined the Reynolds number based on the jet radius, but you can do you can define the Reynolds number based on the jet diameter, only your this number will be changed. Okay. Otherwise everything is same. So, what is important, that this solution is only valid not very near to the jet exit. Okay. So, if you are very close to the jet exit, if your x is less than this times r, okay, so you are very close to the jet exit, your solution is not valid. You can just put these numbers x by r equal to this here, and you will see that it is not valid. Okay. So basically we have a solution of the axial velocity at any location in your domain in terms of the exit velocity of the jet. Okay. And this is at the center line. Okay. R equal to 0 means it is we are on the center line. Okay. So this gives us the center line velocity, normalized center line velocity, and we see that the dependency is based on the Reynolds number, and it is inversely proportional to the axial distance. Okay. It is inversely proportional to the axial distance. So if you go further from the inlet, you see that the velocity will drop, right. That is what we usually expect. Okay. Now we can define some other parameters like the jet half width. Okay. So jet half width is you can define it like this. Suppose you have a jet here. Okay. So half width is the radial distance where the center line becomes 50%, where the axial velocity becomes 50% of the center line velocity, right. So here this is the center line velocity Vx at r equal to 0, and here it will become 50% of this. Okay. And this radius is your half radius. Okay. So this gives us some idea about the jet spreading, right. The half radius, if you can plot it further downstream, you will see that your jet is spreading, right. Your center line velocity will come down and it spreads more, right. So this could be the half radius. Okay. Right. So the jet is spreading. Now we can recover this expression of the half radius from this. Okay. So what you need to do, that Vx will be half of the center line velocity, right. So from this you can get an expression of the half radius. So I am not deriving this, I leave it up to you. So this is the normalized half radius. So there is a dependency on the x location. So it gives, so at any distance x downstream of the nozzle exit. Okay. So that is basically almost close to 3 times 3 by RE, right. And you can also calculate the jet spreading angle, right. So what is the jet spreading angle? So suppose you have the jet here and you connect it through all the points, that is basically your half radius, and this angle is your jet spreading angle. Okay. So I think I have a slide here. Yes. So this angle is basically your spreading angle. Okay. So you can derive one expression of this, and it is simple, as you know, as you see that this is your downstream distance x and this is your r half at that x location. So the angle alpha will be tan inverse of r half by x. Okay. So now if I plot this center line velocities, so this is the center line velocity expression that we already derived, and if I can plot this in the xy plot, and this is basically on the logarithmic scale. Okay. So you need to take a log of this and log of this side, and you see that the slope of this line will be -1. Okay. And if you increase the Reynolds number, it will gradually move in this side. Okay. So now, as I said, that we assumed that Schmidt number is unity, right. So when we assume Schmidt number is unity, so yf and Vx by V, so this is the normalized velocity, these profiles will look very similar. Okay. And then whatever solution of Vx by V you have obtained before, you can equate it to yf, right. So we already obtained this expression for Vx by V, so I am just equating it to yf. Okay. So now you know that the distribution of the fuel mass fractions over your domain, right. this variable, the similarity variable contains the information for both r and x, right. If you know r and x of any locations in your domain, you can calculate this value zeta, and then you can recover the yf at that point. Okay. So, this is the analytical solution that we are talking about now, and so what do you see that yf divided by yf at r equal to 0, like this is the central line fuel concentration, and that should be a function of the similarity variable, right. And this is your volumetric flow rate of fuel, right. So, V times pi r square is the mass flow rate of the jet, and if your jet is pure fuel, then yf is unity, right. Yf is unity. So, qf is the volumetric flow rate of fuel. Okay. So, here you have this expression of qf that you already know, that whatever fuel mass that is coming out, you already know that. Okay. Now, you can calculate yf at any location. Also, you can calculate yf at the center line, just like we calculated the velocity at the center line. You can calculate yf at the center line, and you will recover these expressions. So, it is the same expression that we already obtained, and this is also not valid, very close to the nozzle exit. Okay. So, we have already seen this picture, and now for isothermal jet, we have now recovered one expression for yf in terms of the similarity variable, and here you have the similarity variable. Now, we can draw the surface where the equivalence ratio is 1, right, where the equivalence ratio is 1. So, phi is equal to 1, then your yf will be yf stoichiometric. So, suppose you know that you are sending methane jet in air, so you can calculate yf stoichiometric, right. So, you know that this red lines is basically corresponding to the isocontour of yf equal to yf stoichiometric. Okay. So, now if you know that, you can calculate the flame length, but here actually I call the jet penetration height or something like that, that we can calculate. Okay. So, what I need to do, I will substitute this x by this length Lf. This length Lf is the distance from the center line to the point where the fuel concentration we reach the stoichiometric fuel concentration at the center line. Okay. So, the Lf is the distance from the exit of the nozzle to the point where the fuel concentration becomes the stoichiometric fuel concentration. Okay. So, I will substitute yf equal to yf stoichiometric here and x equal to Lf, and then I can get an expression of Lf here. So, if you closely look at the similarity variable zeta, right, and if I put r equal to 0, okay, we are at the center line, we need to put r equal to 0. If I put r equal to 0, then this variable is also 0, right, then this term will be basically dropped. Okay. And you can calculate your distance Lf. Now, we can also get an expression for the stoichiometric surface. Okay. So, stoichiometric surface is the surface where the fuel concentration reaches the stoichiometric value. Okay. So, we can derive an expression of this, that is there in the subsequent part. So, it is very easy to follow if you can follow this derivation. So, we have the expression of the yf stoichiometric in terms of the similarity variable. Just plug in the similarity variable here, and you have the dependencies on r and x. Okay. And then yf stoichiometric, if you so you take this yf stoichiometric down here. So, this is basically 1, and then you have to do some manipulation, and then at the end you will be getting an expression like this. Okay. So, this is this surface, okay, the expression for this surface. You can now take the example of methane and air, and you can calculate the stoichiometric methane mass fraction. Right. You need to write down the balance equation first, and then from that you can calculate this. So, it is 0.055, and you know the viscosity of air at 300 Kelvin and 1 atmospheric pressure, and if your jet radius is 1 centimeter and the jet velocity is 10 centimeter per second, you can calculate Lf, the distance where your fuel concentration reaches the stoichiometric fuel concentration at the center line. Okay. So, this is one example. So, now we will go to the reacting laminar jet diffusion flames, and if you see here you have the contours of different variables. So, first we have the temperature, and then the C2H4 mass fractions. So, C2H4 is basically a fuel here, okay. And then you have the CO2 that is getting formed, okay. So, if you closely look at that, the temperature and the CO2 goes almost similar, okay, and the CO is characterizing the reaction zone where you have the intense heat release, okay. So, CO is the reaction zone, and O2, so you can see that the O2 is present only on the outer side of the flame. So, this part is the inner side of the flame, and that is the outer side of the flame, okay. So, O2 is only present on the outer side. Within the jet there is no O2, right. So, fuel cannot penetrate the stoichiometric surface, okay, or the equivalence ratio 1 contour, the fuel cannot penetrate, and the oxidizer cannot penetrate. Similarly, fuel cannot penetrate and go towards the oxidizer side, okay. So, this is basically some information that we have, and after that we are going to see that how we can derive the expressions for different concentrations and temperature, okay, in terms of the parameter of interest, okay. So, here also you can see the OH contours, right. Okay. So, this is the jet diffusion flame that we are talking about. So, we have a jet of diameter 2r, and then initially there will be the potential core, but if I take a section away from the potential core, I will be able to see different, I will be able to plot different property, different variables like temperature and the concentrations. So, at the exit of the jet, what you see that again the top hat kind of profile for the velocity, and temperature of the jet and the surrounding fluid may be the same. So, Tf is equal to T infinity. T infinity is the temperature far from the jet, okay, and Tf is the probably the temperature at the jet exit, okay. So, similarly you can plot the species concentrations or species mass fractions. So, Yf, initially you have all the fuel in the jet, right. If you go outside you have the oxidizer, but fuel and oxidizer are not meeting, okay. But you can have some situations where you have the partially premixed jet also, right. You have fuel and oxidizer mixed together. So, that is a premixed jet coming out in a oxidizer. Again the oxidizer can be pure oxidizer, or it could be a burned product, okay. So, you can have a premixed flame before, and you can have a burnt mixture as an oxidizer with some amount of oxygen left in that, okay. So, these are the possibilities which we can have, but now we will stick to the simple thing that we have a pure fuel jet, and that is coming into a pure oxidizer, okay. So, initially you see that Yf and Y oxidizer are separated, they are not coming close to each other. Now, if I plot at a distance downstream, you see that fuel is the fuel mass fraction is changing like this. So, there is a decay, okay. So, initially the fuel mass fraction is to be 1 here, but here it has come down to less than 1, and then this is the point where it is going to 0 almost, and oxidizer is coming from the other side and it is also coming to 0. So, that is the region where fuel and oxidizer are meeting in the stoichiometric proportion, and you are seeing the flame, and you see the high temperature region at that location, okay. So, this is the product that is getting formed, okay. So, basically if you scale down the temperature, then it almost behaves similar to the product mass fractions, okay. If I take another section which is just touching the isocontour of equivalence ratio 1, right. So, what you see here you see so equivalence ratio is 1 here, okay. So, there will be, I expect that there will be no fuel and oxidizer present. So, only thing will be product, okay. So, products are formed here, okay. So, at the center line there will be some amount of product, okay, but here oxidizer cannot exist, oxidizer will be away from this line, okay. So, you see that the oxidizer profile like this. So, it is 0 at r equal to 0, but it is non-zero if you go away from this, okay. Another important thing that when you are forming the product, so product is getting diffused on either side of the flame. Okay. So product will form at the stoichiometric location and it will diffuse to the both to the lean and the rich side. I mean both through the oxidizer and the fuel side. Okay. And if you go on further downstream, then the center line concentration of the product will gradually increase until it reaches the maximum here. Okay. And beyond this, the product mass fraction will gradually decay. Okay. Beyond this, if you go plot here or here, it will not remain like 1, it will gradually decay. Okay. So that is the basic flame structure of the non-premixed flame. We are going to do the analysis of this non-premixed diffusion flame. So the assumptions are that the flow is laminar, steady and 2D axisymmetric, just like before. Fuel from circular port with a radius of r is coming out in a quiescent infinite reservoir of oxidizer. So we are only considering the fuel, oxidizer and product. So fuel plus oxidizer is going to product, okay, in a single step reaction. So inside the flame, right, so this is the inside the flame, inside this red line we have only fuel and products. Okay. So there is no oxidizer cannot penetrate this line. Okay. And on the outside we have oxidizer and product, there will be no fuel left in that. Okay. And you know, at this red line, that is a stoichiometric contour, you get only product, right. So that is the inherent assumption that we are making, although you will see that it may not be the same thing, there could be some amount of little overlap, but that is a good enough to begin. Okay. So fuel and oxidizer react in the stoichiometric proportions, that is the equivalence ratio is equal to 1. The chemical kinetics is infinitely fast and the flame infinitesimally thin sheet, that is the flame sheet assumption that we are making. And the species molecular transport is defined by the binary diffusion, and thermal and species diffusivity are equal, right. So the Lewis number is unity. In the previous case we assumed the Schmidt number is unity, but here we are assuming the thermal and the species diffusivity are equal. So Lewis number is unity. So all the species have the same diffusivity that we are assuming. So no radiation, only radial diffusion, axial diffusion is neglected. Okay. So if you see this, then here actually you can calculate the equivalence ratio at any location if you can measure the mole fractions at that point. Okay. So you can first calculate the stoichiometric oxidizer fuel ratio from this equation, right. Now if you can measure that at this point you have some amount of hydrogen and the H2O, so there could be no O2 here, right, only hydrogen and H2O can be present. This is the inside the flame. Okay. So you have measured the mole fractions, so you can calculate the equivalence ratio. Okay. So this is a simple exercise that you can carry out. So now this is the governing equations, so the equations are similar, right. So we have the mass conservation equation and then the species conservation equation, and we are assuming the flame sheet assumption, that is the m dot I triple dash is 0 everywhere except the flame sheet. So only at the very thin region we have the reaction rate, otherwise it is 0 everywhere. Okay. So discontinuity at the flame sheet. Okay. At the flame sheet there is a discontinuity, and the inside the flame we have the fuel and the product, and the outside we have the oxidizer and there is no fuel and there could be some product. And outside the flame you can calculate the product, and I mean the product you can calculate, that is basically 1 minus YF minus YO. Suppose you are inside the flame, there is no YO, right. So you know what is YP. Suppose you are outside the flame, there is no YF, so YF is 0, so you know what is YP. Okay. So this is the axial momentum conservation equation, and this is a special term that you need to consider. This is the buoyancy term. Okay. Similarly, the energy equation, and we are taking the Schwab-Zeldovich form, and then we can simplify this, right. We have assumed that all the species, we can assume that all the species have the same specific heat and all, and then we can simplify this. Okay. So if you see these equations, you have some unknowns, right. The unknowns are the radial velocity, axial velocity, and then the fuel mass fractions, oxidizer mass fraction. The product mass fraction you can recover from this expression, right. Otherwise YF and YO are unknown, Also the unknown is temperature T, right. So the unknowns are listed here, Vx, Vr, temperature, Yf and Yo. These are the 5 unknowns, but there is a discontinuity at the flame, right. So boundary conditions for species Yf and Yo and energy and the energy equation, that is the temperature, are required to be specified at flame, okay. But we cannot specify the boundary, right, because we do not know it, okay. So we do not know where the boundary, the flame boundary is located. So that is a problem that we encounter here, but we did not get the same problem when we talked about the non-reacting jet. But for the reacting jet, there is a discontinuity at the flame, and therefore we need to specify the boundary conditions at the flame, but we do not know the location of the flame. That is the problem, okay. So what we need to do, but we have the other boundary condition, right. At the flame axis r equal to 0 at any x location, we know this axisymmetric condition will be applying, and then far from flame, that is r tends to infinity, we know what is the boundary condition. So there only you will get the oxidizer and the velocity will be 0, right. At the nozzle exit we know the top height profiles, but at the flame surface there is a problem. So now we need to do some other trick to come out of this, okay. So we will do the conserved scalar approach, okay. Now I will explain what is this. So conserved scalar is any scalar property that is conserved throughout the flow field, okay. So it is conserved throughout the flow field. So what do you mean by conserved? That it can either get advected or diffused, it cannot be produced or destroyed, right. So that is the conserved scalar and does not have any source term in conservation equation, right. So it is just temporal, advection, diffusion, balance. So there is no chemical source term, okay. So that is the conserved scalar. Now conserved scalar approach greatly simplifies the solution of reacting flow problems, especially for the non-premixed flow, okay. So we can define this conserved scalar based on our requirement. So one of the conserved scalar could be the standardized enthalpy, right. You all know the standardized enthalpy, Professor Argode introduced to you that thing. So I am not going into that, but if you write down the transport equation of the conserved, the standardized enthalpy, you will find that there is no source term, and that helps, okay. So that is a conserved scalar. So you can write down the transport equation in this manner, okay. So you see that this is a steady state expression, so there is no temporal term. We have the axial term, radial axial advection, radial advection, and there is a diffusion term, radial diffusion term. We have neglected the axial diffusion, right. So you see that there is no production of enthalpy, standardized enthalpy, right. Similarly, you can define the mixture fraction, right. So mixture fraction, the definition is given here. So it is the mass of material that is having origin in the fuel stream, okay, and that has to be divided by the mass of the mixture. So suppose you can measure at any location what is the mass of material that has been coming out, that has been originated from the fuel stream, and if you know the total mass of that mixture at that point, then you can calculate the mixture fraction, and there is a simple expression of the mixture fraction. So it is given here. So Yf, right. So here we are assuming that the jet is pure, okay. So all the mass is coming from the whatever Yf is there at that particular point, that has been originated from the fuel jet, okay. Also there is some reaction, okay. So oxidizer, there was no oxidizer, so it is 0 times Yo, and then there is another term. So what is this? This Yp is the mass fraction of the product, okay. Yp is the mass fraction of the product, and so how the product has formed, there is a chemical reaction, fuel plus oxidizer went to product, right. So what amount of fuel was present that caused that product. So you can calculate that and you will be able to get this expression, okay. So this is the expression of the mixture fraction, and then you will see that one important observation, that in the fuel stream, right, Yf is equal to 1, there is no product, and F is equal to 1. Similarly, if you go to the oxidizer stream, then Yf is 0 in the oxidizer, there is no oxidizer, and there is no fuel in the oxidizer stream, and there is no product. So F is again 0. So everywhere else the mixture fraction will vary between 0 and 1, okay. So we can obtain the mixture fraction from the elemental mass balance, okay. but I will quickly go through this. So we do not have much time to cover that. So yeah, for example, if you can measure the mole fractions of different compositions at any location, and then you can write a simple expression of mixture fraction using the mole fractions. Okay. So MWC is the elemental mass fraction of the of carbon, right? MWC, that is elemental mass fraction of the carbon, and MWH, no, sorry, this is the molecular, so atomic weight of the carbon, and this is the atomic weight of the hydrogen, right? So you can calculate the elemental mass fraction, and then from that you can define mixture fraction accordingly. Okay. So this is one expression, and you know the molecular weight of the mixture is there because there is a mass of mixture. So you get a term like molecular weight of the mixture, and that you can easily recover if you know all these compositions. Right. Again, you can calculate the you can obtain a ratio between the equivalence ratio and the stoichiometric mixture fraction. Okay. So stoichiometric mixture fraction and the equivalence ratio, and this is the local mixture fraction. Okay. So there is a relationship that you can easily figure it out. Now we have already seen this. So if you write down the transport equations, so the fuel, the transport equation of the fuel concentration, you have this expression. So there is a volumetric production term m dot f triple dash, and now this is the transport equation of the product. Okay. So you can write down the expression, and then this is the volumetric production of the product. So here it is destruction, here it is production, right? So if you divide this the equation by this expression, stoichiometric oxidizer fuel ratio plus 1, then you will get this equation, and then you club it together, this one plus this one, and then you get an equation where you see that these volumetric terms are not present. Okay. Because whatever m dot f is getting consumed, some amount of proportionally there is some amount of product formation, right? So that they will cancel each other and it will be 0. Okay. So this is the transport equation for a conserved scalar, and we can say that this is a mixture fraction, and several other definitions can also be possible. You can write a combination of YF and YO, you can write a combination of YF, YO and YP also, right? You can play it around and you can get different expressions. Okay. The advantage is that we do not have any chemical source term here, right? And then we can do the similar treatment that we have done for the non-reacting jet problem. Okay. So we recover this expression, and then we have the boundary conditions like this. Okay. Now we can solve it numerically, or we have the analytical solution in terms of the similarity variable. Okay. Similarly, you can write down the standardized enthalpy equation, transport equation, and again here is no source term. Okay. And these are the boundary conditions. So in the fuel stream, the enthalpy, standardized enthalpy is YFE, and in the outside the standardized enthalpy is the HO infinity, right? So we need to have expressions of this standardized enthalpy, and then we can proceed further, right? So what do you see, that this is the axial momentum conservation equation, and if you neglect this term, if you neglect this buoyancy term, and if you can normalize this, so they will be just similar to the previous equations like conserved scalar equations, right? If you see, they are almost they're same actually. Okay. So we have the axial advection, radial advection, and the radial diffusion. Similarly, here in the axial momentum equation, you have the same terms if you neglect this last term. Okay. So now we have some simplifications we have done, and we have arrived the transport equations of the axial momentum, and then the mass fractions equations, and then the mixture fraction and the standardized enthalpy. And if you can normalize this in this fashion, all these equations will collapse to a single equation. Okay. So you can normalize this by this fashion, and you will recover a single equation like this. Okay. So this is one single parameter, okay, that we need to solve, and if you can solve this, you will recover all other variables like this. Okay. If you know the solution of this variable, you will know what is Vx star, what is f, and what is h star. Okay. So these are the boundary conditions for this generalized variable, and we know that it is 1 here and 0 outside of the jet, and the symmetric condition at the center line, and if you go far from the jet center line, it is 0. So this, now you can solve this using the similarity variable approach, okay, or you can do it numerically, whatever you like, and then yeah. So I have now written it in terms of the f. Okay. So this similarity variable can be also written in terms of f, right? This that parameter is just like f. So this is the transport equation, and now we need relationships like this. Okay. We need to know what is yf in terms of the f. We need what is yo in terms of f, right? Yp will come automatically. We know, we have seen some slides back, and we also need to know that what is the temperature in terms of f. If we know all this, then we know what is density in terms of f, right? And density is needed if you have to solve the continuity equation. I mean, it is related with the continuity equation. So what you can do, if you know all this information y and t, you can calculate density, and then that will be fed into the continuity equation, right? So these are the boundary conditions of the mixture fraction, and inside the flame the mixture fraction is varying between f stoichiometric and 1. Outside it is varying between 0 to f stoichiometric. Okay. I mean, it cannot be equal to f stoichiometric. This is a stoichiometric mixture fraction line where the flame is located. That is basically equivalence ratio 1. Okay. So now we have identified there are two different locations. One is inside flame, one is another is the outside of the flame, right? So inside of the flame we have this condition, and we know that there is only fuel and product, right? So Yp is basically 1 minus Yf, there is no oxygen there. Okay. So now you can recover Yf. Okay. So Yf is known, right? So this is the expression of the Yf inside the flame. Okay. So that you can follow from this expression. Okay. You can simplify this and you will get Yf as this. Inside the flame there is no oxygen, so Yo is 0, and Yp is the rest, so that is 1 minus Yf. You can calculate what is Yp. So we know what is inside the flame. Similarly, from this we can calculate what is outside the flame. Okay. So outside we know we have oxidizer and the product. Okay. So fuel is 0, so Yf is 0 at the outside of the flame, and the oxidizer you can calculate, and that is 1 minus f divided by f stoichiometry, and the rest is the product. So you can calculate from this. Okay. At the flame we have only product, so all of them are 0 except the product. The product is 1. Okay. So these are the simple state relationship of this fuel mass fractions in terms of the mixture fraction. Okay. So when we know this, but still we do not know what is the temperature. So we need to know that what is the temperature, right? So again you see that the non-reacting and the reacting, if you assume that constant density, the flame surface will be almost similar, you know, and the flame length will be similar. Of course that is the constant density, but if you take the variable density, then it will be different. Okay. So density is equal and it is not changing, it is uniform everywhere. That is the assumption. Now we need to calculate what is the temperature, right, in terms of the mixture fraction. So first we start with the standardized enthalpy, and right, we know that enthalpy is summation of yi times hi, right. So yi is the individual mass fractions of the species multiplied by the species enthalpy, and we are assuming that the specific heats of each species are constant and equal. Okay. So all the species have the same specific heat, because we want to simplify our life. Okay. Also the heat of formation of products and oxidizer are 0. So heat of formation of the product and oxidizer, it is, we are assuming it is 0. Then the enthalpy of formation of fuel should be equal to the heat of combustion of the fuel. Okay. So we can write this expression. What you need to do, you need to expand this HI in terms of heat of formation plus sensible enthalpy, right. If you can expand this, then you will be able to recover this with these assumptions. Okay. So this is the expression of the standardized enthalpy, and you know there is another variable YF, which we have just found the relationship of YF in terms of F, right. So YF is a function of F. Okay. So now we need to know what is T as a function of F. So what we do, we start with the normalized enthalpy, and we know that normalized enthalpy just behaves like mixture fraction, right. H star just goes like mixture fraction. So what is H star? H star is this expression. So H is the local enthalpy minus enthalpy of the oxidizer divided by the enthalpy of the jet minus enthalpy of the oxidizer. Okay. And now with these assumptions, you can write what is the enthalpy of the oxidizer. Heat of formation is 0, so only the sensible enthalpy part is present. In the fuel, there is a enthalpy of formation, that is basically the heat of combustion plus the sensible part. Okay. So we know these expressions now, we can plug in there, and if I plug in, then this is H star what I obtain here, and this H star goes like mixture fraction. Okay. So now we have seen that YF goes like mixture fraction, right, and there is also a mixture fraction here. So therefore T has to be a function of mixture fraction, right. And if you now put what is inside the flame, so inside the flame we have YF at some quantity, Y oxidizer is 0, Y product is there. So now we know that what is YF inside the flame. You recall that we have derived the expression of YF inside the flame. Okay. If I substitute that, then I will get temperature explicitly as a function of F. Okay. So again we start with this expression which I had in the previous slide. If you can solve this, you will get this expression. So T temperature in terms of YF and F. Okay. So now inside the flame we know what is YF, so you just put that value here and you will get the temperature as a function of F. T is a function of TF, and that is basically this. Okay. So how it is varying inside the flame? What is the variation, whether it is linear or parabolic or cubic? How it will vary? It is a linear expression, right? All these are constant, so it is a only function of F. At the flame we have only product, so you can recover, so YF is equal to 0, so from that you will get this expression, and F is equal to F stoichiometric. So you substitute F equal to F stoichiometric, YF is equal to 0, then you can follow from here to here, right. So outside the flame we have only oxidizer and product. Okay. So again from this expression, okay, we can derive this. Okay. So these are the expressions of temperature in terms of the mixture fraction. So earlier we have derived the expressions of the species mass fractions in terms of the mixture fraction. So now I have derived temperature as a function of mixture fraction. So when we know temperature and species mass fraction, we can get the density from the ideal gas law, right. So this is one example which I am skipping at this stage, and then yeah, this is same expressions, right. So now I can plot this whatever we obtained. So inside the flame YF varies like this, right, outside the flame Y oxidizer varies like this, so I can just plot it. Okay. So the first line is basically so this is basically Y oxidizer, so it is 1 here when the mixture fraction is 0. So mixture fraction 0 means it is in the outside of the jet, that is in the co-flow or the ambient. So it is 1 here, Y oxidizer, and then it goes to 0 at the stoichiometric mixture fraction, right. On the other side you have the fuel mass fraction, that is 1 unity there at F equal to 1, and then it comes to 0 at the F stoichiometric. Now you have the product. So what we have seen that Yp is equal to 1 at the F stoichiometric, there is only product, no fuel and oxidizer. So it is 1 here and it goes to 0. So basically you can just plot these expressions, right, plot these curves and then you will be able to get this. Now you have also derived the expression of temperature, right, we have in the previous slides, we have derived the expressions of the temperature, right, this one and this one, we can plot it. So this is the flame temperature that is occurring at F stoichiometric, okay, and this is the temperature at the oxidizer and this is the temperature at the fuel jet, okay. So this is the simple relationship. So what do we see that if I know mixture fraction, I can recover everything, I do not need to solve any other equations, right. Only thing we assume something, we assume that the fuel plus oxidizer is going to product, and there are many other assumptions which I have listed, but the benefit is that if I know mixture fraction, I can recover all other parameters. Then from that I can compute the density and then I can solve the continuity equation and momentum equations, I can get the axial and the radial velocity, right. So it is simple. So we do not need to solve n number of species conservation equations, okay. That is one advantage of the mixture fraction approach. So here are some solutions like the flame length, right. So the flame length is basically almost the same expression which we have derived for the non-reacting case. Only thing here you need to substitute Yf stoichiometric and here you have the Qf. There actually we did in terms of velocity and then of course for the Yf also you have derived. So this is the flame length assuming constant density. Again you can consider the variable density and for that there is some expressions. I think these are available from the literature and it is available in the book of turns. So you can just, if you are interested, you can go through that. But what is important is that the flame length is proportional to Qf and it is inversely proportional to the diffusivity and it is also dependent on the stoichiometric mixture fraction, fuel mass fraction, okay. So if you change your fuel, your flame length will change, right. If you increase your the fuel flow rate, then also your flame length will change. If you double it, it will double, okay. So this is simple expression what we have obtained. We will see after some time that how the flame length actually varies with the flow rate. So in the laminar regime, so flame length varies like this, okay. It varies like this, and then after that the flame length there is a transition. So laminar to turbulent transition there will be. So actually it decreases little bit, and then it remains constant in the turbulent region. So that is one observation that we can do if I do the similar analysis with a turbulent flow in the background, okay. So for the turbulent non-premixed flame, the flame length is independent of the volume flow rate or the jet velocity, okay. For the laminar case, it is linearly varying with the fuel flow rate or the jet velocity whatever, but here actually, I mean if you plot the jet velocity or Reynolds number, so it is basically linearly varying in this region, and then after that after transition it becomes constant. So this is the turbulent region and this is the laminar region, and this is basically your transition, okay. So now we will quickly see what is counterflow diffusion flame. So this type of flames are important, as I said, if you want to quantify how the flame structure looks like, right. You can do simple experiments of the fuel and oxidizer, they are opposing each other, and you can set the flow in, and depending on the, as I said that if the momentum of these two streams are equal, then the stagnation point will be located here, but the flame will be located depending on the stoichiometric, right. In the most of the cases it is towards the oxidizer side, but if you have some fuel, special fuel, then probably it will come towards the fuel side, okay. But what is important, so this is a stagnation point, right. So velocity along this line will be 0, right. So there will be no flow inside, but how the fuel is diffusing, I mean how the fuel and oxidizer is coming into contact, that is the important thing that we need to know. So there is no fuel, that is, I mean there is no advection, right, the velocity is 0. So only the molecular diffusion is taking place, and due to this diffusion this fuel is diffusing into the oxidizer, and then at the stoichiometric location the flame forms. Okay. So we can carry out the analysis of this type of counterflow diffusion flame in the very simplified manner, like. So again we can use the stream functions, and then from that we can derive it, right, and it is a long derivation, so I will not go through that. So you need to write the x momentum equation and the r momentum equations, all the stress terms are there, and then you will get in one expression like this for the axial advection and the axial and the radial advection terms, and then you can do for the x momentum equations other terms like these terms. So I will skip through. So these are momentum equations. Okay. So x momentum equation finally it takes this form. So you initially start with the PDE and then you can reduce it to the ODE. Okay. So these derivations is in the slide. If you are interested, you please go through that. So it becomes ODE. Similar treatment you can do for the r momentum equations, and then again it becomes an ODE. Okay. Okay, so finally we have this many unknowns, okay, and we have reduced it to f and g. I mean we have some variables, and you can solve these equations now. Okay, so these are the resulting equations, like the energy equation and the species conservation equation, and with proper boundary conditions you can solve them, right. Okay. So these are the ideal gas equation and the relationship for diffusion, mass fluxes, and all this. And finally, if you solve it numerically, you will be able to get a flame structure. Now what you see that along the x axis, so this is the methane side, the fuel that you are sending, and that is the air side. So air is oxidizer is coming from the other side. Okay. The stagnation point will be located at an appropriate location, right. So if the momentum of these two streams are equal, then it will be located at the midway, but you know that methane is lighter than the air, right. So you see that the stagnation point is located towards the methane side. Okay. So this is the stagnation point where you see the velocity. So initially the velocity is the exit velocity is 50 meters per second for the both stream, right. So it has come to 0 here, the velocity is 0. So this is the stagnation point, and then it goes to again on the minus 500, the other side. So air is coming from the other side, velocity is minus 500, it is going there. But you see that the flame is located towards the air side. So this is the stagnation point, but the flame is located here, right, around 0.75 or 0.8. Okay. This is the location of the flame. Okay. And here you see that there is a change in velocity. What could be the reason of that? So if there is no reaction, you would expect that this is a stagnation point and then it will go to the air velocity there. Okay. But why it is happening like this? Yeah, because of the change in density due to the temperature, high temperature. You see that there is a peak and trough. Okay. So equivalence ratio, as I said that in the methane it is a pure fuel, equivalence ratio would be infinity, and here the equivalence ratio at air it will be 0. So the variation will typically look like this. Okay. So some other species, so CH4 is diffusing from the other side and O2 is diffusing from the other side. So you see that CH4 is like this, it is going here, and here also you see that O2 is almost 0. Okay. almost 0. Okay. So there are some other radicals around this. So now we have seen that for the laminar premixed frame we can write down the conservation equation for a conserved scalar. So conserved scalar is mixture fraction. We were talking about F earlier, I think I should change it, so it should be F or mixture fraction, right. So what do you see that the jet is coming, so mixture fraction is unity here and the oxidizer mixture fraction is 0, and then you see the iso lines of different mixture fractions. And what is the purpose of all this? So why should we know mixture fraction? Because if we know the mixture fraction, we know we can calculate other variables of interest, right. So one is the no reaction. Okay. So in this case you see that all the species mass fractions, how it changes with the mixture fraction. Okay. So if there is no reaction, your fuel will be maximum there in the jet, right. If it is a pure fuel, then it will be unity there and it will go to 0 in the pure oxidizer. Similarly, oxidizer will be 0.233. If you are using air as an oxidizer, the oxygen mass fraction will be 0.233 here, and then it will go to 0 in the pure fuel. And this is the variation of nitrogen, it will be 0.6767, right, 0.233, 1 minus 0.233 is 0.767, and then it will go to 0 at mixture fraction equal to 1, right. So temperature will be same. So this is basically the mixing profile what we have used. So if the both streams have the same temperature, then the temperature will be same. If they are different temperature, at different temperature, then you can just join a straight line between these 2 points, and that is the no reaction, only mixing. Another is the first chemistry, right, fuel plus oxidizer is going to product. So here you have the oxygen profile and the fuel profile is varying like this, and the stoichiometric point you see that there is no oxidizer and fuel, only you have the product. So this is the product mass fraction and the rest is nitrogen, okay, that you can plot, and temperature is like this. So it will be just like the product, and you now know that what is the expression of these lines, right. We have done the simplified analysis and we know that variations of oxidizer, and we also know the variation of the fuel and the variation of temperatures in the inner and the outer region. Okay. So we know this. So this is the first chemistry. Okay. So fuel plus oxidizer is going to product, but in actually what we see that we do not get the first chemistry. So there is some rounding that takes place near the stoichiometric location. So for the hydrocarbon flames, so suppose it is a methane flame, you see that near the stoichiometric, okay, so there the temperature is not linear. So if you see that it is almost linear here, right, almost linear, but in this region you see that there is some rounding that has taken place. Okay. That is because of the equilibrium, these chemical reactions, the equilibrium that we encounter. Also we see that the oxygen, it should come to 0 here, right, but we see that a very little amount of oxygen is still left. Similarly the fuel. Okay. So when we know these profiles, we can easily calculate the flow field, right. If we know the mixture fraction, then we can calculate, we can obtain this species concentration and temperature, and we can easily calculate density and obtain the flow field. Okay. So that is the advantage of using mixture fraction. So you are solving only the Navier-Stokes equation plus mixture fraction equation and recovering all other variables in terms of mixture fractions. As I said, the counterflow diffusion flame, if you can do the experiment and you can measure the along the streamline the concentrations of different species and temperature, you will be able to see that these variations, right. So you see that probably this is the fuel side, no, this is the fuel side. So fuel is coming and it is almost 0 in the flame front, and then at the flame, and here the oxidizer is coming from the other side and it is almost 0 here, and temperature is represented by this black line. But these are all along this physical coordinate system, right. So this side is fuel, this side is the oxidizer. Okay. But now we can plot the same data in the mixture fraction line. in the mixture fraction space, right. So, here you see this is the mixture fraction variation. Okay. So, it is 0 in the fuel and it is going to 1 at the mixture fractions at the fuel stream. Okay. So, 0 to 1 it is varying along the physical direction. Now, you can plot all these species mass fractions and temperature along the mixture fraction space. Okay. Just need to manipulate this data. So, the same plot I am making in the mixture fraction space, then we will be able to see the nice flame structure that we have so far discussed. Okay. So, this is the equivalent plot. Only thing except the physical, I mean in place of the physical coordinate, I have replaced the physical coordinate by the mixture fraction space. Okay. All other information are same, and we see that we get a familiar structure, what we have seen for the equilibrium chemistry, right. Here we have the oxidizer, now the fuel is coming from the other side, and you see the high temperature here that is forming near the stoichiometry, right. So, these two data are basically the same, only I have changed the x axis. So, instead of the physical coordinate, I have replaced it by the mixture fraction. So, I will stop here, and if you have any question, then I can answer.